All right. I just do not want people to miss any of the class material, so I decide to record today's lecture as well. Okay, let's start with our lectures. First of all, it's some review of what we learned last week. I just want to highlight some of the important things. I know that we introduced lots of things from last lecture, but this I listed here are the most important things. And when you work on the homework, you will also realize those are the things you are going to use a lot. So first of all, how to write a sample space. That's you just write out. Sorry. All possible outcomes of the experiments. And an event is just a collection of the outcomes from the sample space. So it's just a subset of the sample space. And we talked about what is complement, what is union set, intersection of different sets, disjoint sets. And we'll cover a little bit more here in the next slide. And these three axioms of the probability, these are important because you are going to use this a lot, which is for any event, the probability of it would be always between 0 and 1. And the probability of your whole sample space would always be 1, because that's all possible outcomes already. So the probability of it would be strictly 1. If this event A1, A2, A3, etc., is an infinite collection of disjoint events, then their union, the probability of their union, see, they are disjoint events. So the probability of the union of the sets would be a summation of their individual probability. A bit more on the union and intersection operations. Like the probability of A plus the probability of the complement of A would be 1. And this formula you will use a lot. And the probability for n equally likely events, their probability are just 1 over n. And the probability of event A is the number of the output containing A over n, where n is the total number of events, total number of outcomes. Product rule. This you will also need to use. It's just the one technique for you to calculate the probability. And for permutation, we have this formula for a combination. This is how we do the calculation, where this is n choose k, and this is permutation of k elements out of n total elements. And conditional probability, this one, you will see this as well. And for the independence, the definition is like this: if and only if the intersection of two sets, probability of the intersection of two sets equal to probability of event A times probability of event B. That means by looking at this one, that means the probability of A given B is just simply probability of A. Like the information about B have no effect on A. So that's why we can just remove this B or directly write as this. And this law of total probability. So when we do the lecture, I kind of skipped the example because I saw there was some problem with the statement. But here I put the formula here first. I want to go over this example again. I just want to make sure that people know what this, how to use total probability. So let's read this together. You are in a tennis tournament where the probability of winning is 1 against half of the player. We call the half of the player as group 1. So the probability of winning is 0.4 against a quarter of the player, which we name it group 2. And 0.5 against the last quarter of the player, we name it group 3.
162.
Opponent, what is the probability of winning? So this is asking the probability of winning. And let's collect what information we have got from this statement. Define A being the group that you play against. So that's our AI. We have A1, A2, A3, right, against group 1, 2, 3. So the probability of you meet each group is listed as here. So you play against group 1, the probability you meet them is 0.5. Why? I highlighted the half of the player is in group 1. And for group 2 and group 3, each have a quarter of the players. So when you randomly choose from the people you are playing against, then the probability you meet the group 1 would be 0.5 because group 1 have half. Oops. Oh, I thought you can always see my screen. So probability you meet group 1 is 0.5, and for the group 2 and group 3, each have a quarter of the player. So the probability you play against group 2 and group 3 are each 0.25. We want to calculate the probability you win. We define this event as B. And we know that if you play against group A, so given that you meet group A to play against, the probability of winning against group A is 0.3, which is given here. So given that you meet group 1 to play against, the probability of winning is 0.3. This is what is stated here. Probability of winning is 0.3 against half of the player, which is group 1. Similarly, you can write this conditional probability given this A2 is 0.4. So, okay. I saw, well, yeah, so this given A2 is this probability, and given A3 is this. This is what is telling you in this statement. So this is a conditional probability. Given that you meet group 1, the probability of winning. Given that you meet group 2, the probability of winning. And group 3. So we want to calculate the probability of B. And we know from the law of total probability, we can decompose this probability of B by this sum of this multiplication of conditional probability with each of this conditional event. Yeah, I think the very last step is the easiest one. The hard part is that you can extract the information from the statement. Like, how do you define the events? How do you get like this conditional probability? And once you get all these elements, you just apply this formula, you can get the probability of what you're trying to calculate. So this is the law of total probability, and this is also one of the most important concepts in chapter 2. conditional probability. So just recap again, this is a conditional probability. And I want to go over this conditional probability example, like in the very end of the our chapter 2 slides. Well, this is one, I should say this is the advanced problem or example question for the conditional probability. In the homework, I think they are easier comparing to this too. Let's just read this together again. Medical records reveal that of 937 men who died in a particular region in 1999. So we know the total number of people who died in this region. And out of this many people, 212 of them died of causes related to heart disease. So we know this many people, they are died because of heart disease, related to heart disease. And 312 of them had at least one parent with heart disease. And out of this 312, with at least one parent with heart disease, 102 died of causes related to heart disease. So if we randomly selected a man from this region, we want to get the probability that he dies of causes related to heart disease, given that neither of his parents died from heart disease. So we know this is a conditional probability. It's given that neither of his parents died from heart disease. So again, let's do some information collection from this statement. Well, I have posted everything here, but this is like step by step. This is what you should do. By reading a statement, you should first trying to define some events that you know from this statement. So if we define this H being the event that at least one of the parents of a randomly selected man, yes. Oh yeah, sure. Yes. Of a randomly selected man died of causes related to heart disease. So I highlighted this. At least one of the parents died of causes related to heart disease. And then the complement of H would be the event that neither of the parents of a randomly selected man died of causes related to heart disease. So this is one key point, that the opposite of at least one is none. So neither of the parents of a randomly selected man died of causes related to heart disease. So we know the question is asking conditional on this H prime. And again, we define this D as the event that a randomly selected man died of causes related to heart disease. So this is directly related to heart disease. And this is what we want to calculate. So I think for this type of question, you would always want to go back and read it again and again, because that's the way how to get the information from it. How do you understand like this? If we randomly select a man from the region, what is the probability that he dies of causes related to heart disease? So this is our event D, given that neither of his parents died of heart disease. That's the event H prime, right? So we are calculating this probability of D given H prime. Well, how do we get this? So for this kind of complicated question, there are two ways. You can either use a Venn diagram or use a table like this. Well, I personally prefer this one because, well, many people like to have this intuitively visualize the portion out of the sample space. But let's look at this one first. So, well, once we define this D, H prime, and when you write it as a table, you always want to make it a square. So on the horizontal, like on the rows, you want to do H or H prime. And on the column, oops, well, I said it opposite. This are the columns, these are the rows. But this is horizontal, this is vertical. You just put D and D prime in one direction and H prime in another direction. And you want to put the numbers, those numbers listed here into those cells. See which one corresponding to which. It's always like in this right lower corner, it's always the total of your sample. So that's 937. This should be the first number you write it on this table. So, and also we know this many people died of causes related to heart disease directly. So that is our D. So we write it here. And to this end, it's the sum of these two cells. We write this one first. And out of those people who died of heart disease, at least the one parent, there are 102 of them have at least one parent. Oh, sorry, let's ignore this first. This is the second number that I put on this table. So I told you this is the first number you put there, this is the second one. And the third number, when you read the statement, you find 312 of the men had at least one parent with heart disease. So this would be the third one, where to put it. So, oops, yeah. So this one is corresponding to like at least one parent have heart disease. So this is where we put the 312. So this first, the second, this is the third, and the last number that we were told is that out of these 312 people, at least one parent with heart disease, this many died of causes related to heart disease. So this number would be a part of this, like directly have heart disease caused their death. So this is where we put this one. So once we have these four numbers out here, now we can look for what is the probability of D intersected with this H prime. Like this is the sum of these two cells. So you can get this one is 110. And well, we know that this conditional probability is this over this probability of H prime. So we just need to find what is the probability of H prime. So which is, you take another subtraction from, we subtract this from this, you get this number. So you just get these two cells and you get the conditional probability. So this is the very detailed like steps when you read a statement and how do you make it into a probability table and to find the probability you want to calculate eventually. Okay, yeah, I think that's all the recap for the previous lecture. And I think the homework 2 is not that hard. I got some questions about homework 1, and yeah, people still trying to get ask questions from Blackboard. But that's not recommended to use Blackboard directly. But use, if you want to get immediately help or get the help as soon as possible, it's better to just contact me by email. Or today, when I checked the web assign, I find also people trying to use the ask your teacher function in Yeah, and today I subscribed to that function from Web Science. So in the future, if you want to do that, that's fine. But yeah, for the past week, I didn't subscribe to it, so that's why I'm kind of delayed on answering the question there. Yeah, either send me email asking questions or use the ask your teacher function from the Web side, because that will list you which question you are asking specifically, which small question you are asking. So that probably will be easier for you to describe what your problem is. I'm sorry.
Could we go over the problem on homework too?
On homework too?
Yeah.
Like right now or?
Oh, yeah. I mean, if it's okay. Or
Well,
think
I don't know if people have already worked on that or
Oh.
not. Yeah, maybe it's not fair to for people who have already like worked on for their own like worked on their own, or if we go over it, people just know the answer. Yeah, but you are always welcome to ask questions. Like I know people would have several submissions, like before they really get the score on the question. So if we tried, I remember it's 3 submissions.
Yeah, they let you submit each question
3 times.
but I haven't had it.
Okay.
Problems with it, it just updates and takes the highest score.
Okay, yeah. But I think if you are hesitate about your last try,
Pretty sure it's up, because that's how it was trying to.
oh really?
And it's do like 3 attempts and like the fourth, and kind of takes things off.
Oh, so if you use all 3 submissions, then it takes.
Yeah.
Oh, this is
No, not. You did one?
Yeah, because like it tells you to submit each question individually, and then you submit the whole thing at the end, so maybe that's what it is, submit the whole thing, but I didn't see any points taken off whenever I would submit to see if something was right,
okay.
and definitely.
Okay, but I think the best practice would be
Yes.
you try it 1 time or twice, and you are not really confident with your last try or last 2 tries, then go to the either discussion board, or discussion board is more of an interaction between students. I will also go there to check if there are problems asking there. Well, that's normally how we do. Like when we do the homework, we find, okay, this is not so, I'm not so sure about this. Let's discuss with my classmates. Or eventually I would have to ask my teacher about this. Yeah, so get help. Yeah, that happens. Well, yeah, let's go to our chapter 3, which is the main content for today. Well,
Are they gonna be more like part or like problems
like in chapter 2, are you asking about chapter 2 type of homework?
Will the questions on the test be more like about the science words, or will they be more like the example?
It's more like on level side. Well, yeah, this is our topic today, the discrete random variables. Yeah, I was about to say that, to be honest, chapter 2 it can be really hard. Also be easy, as long as you know the basic concept and you can do some basic and like medium level questions, you're good to go. You don't need to be a pro like doing the really hard probability questions. And I think chapter 3 and chapter 4 is relatively easy comparing to chapter 2, because there are just too many of concepts and terms in chapter 2. Well, that's statistics. Okay, So in this section, in chapter 3, we're going to cover what are random variables and what are PMF and CDF. Those will make sense in a second. I'll talk about that. What are expected values and what are variances? And we will talk about some of the discrete probability families. And today we will also go over a little bit of R with a homework question on homework 3 questions. Before anyone worked on it, we will talk about one of it. Let's talk about the first concept here. We have already defined what is sample space, and we put all possible outcomes in our sample space. A random variable is a function that finds a numerical value for every event, every outcome in your sample space. Find a numerical value. So it's more like a mapping thing. A random variable would map your sample space to a numerical value. So in math term, a random variable is a function from the sample space to real numbers. That's what I mean by a mapping. So we generally use uppercase letter to denote random variables. We use a capital X or capital Y, and a realization we would use like the lowercase small x, small y. To understand what is a random variable, I have a small example here. So you think of your sample space as all the fish in the sea. See that your random variable is that how long is the fish? So sample space are all the fishes in the sea. And the random variable you're trying to capture is how long the fish is the fish. Before you get a fish, it's still a random thing. Before you get it, they're still in the ocean. You don't know how long is the fish you are going to get. So you are still living in the math lab. All the possible values are out there with different probability of occurring. So you pick a fish, it can be this long or that long. It's random. Once you pick the fish, you've moved out of this math land and generate data. This is called a realization of a random variable. Before you get it, it's all random. It's right there with the probability of getting different lengths of the fish. But once you pick one, you get a realization of a random variable. This random variable can be like quantitative, like numerical, or it can also be, it can be discrete or continuous. Like discrete example would be the number of siblings you have, but we know already, like for each of you, you know like the number of siblings you have, but before I know any of you, so it's a random variable. But if I ask one of you how many siblings you have, you tell me how many, and then that's a realization for one student. Example for continuous random variable is the time your commute took today. For me, it's really long for today, but it's a continuous. It can be anything greater than 0. It's numeric, it's continuous value, so it can be like 13.5 or 1.5, 2.5 hours, like that. So an event can look like this, being a random variable, x greater than 4. This event A is the event that you have more than 4 siblings. And event B is that the commute time is in between 2.3 to 4.2 hours, like that. So now with the random variable, this is how you write the event. It will be like this. So once we get an event, we will want to find its probability. Now we have the definition of the probability mass function. This is typically shortened as PMF, and it's one way to characterize discrete random variables. So this is for discrete random variables. It assigns probability to the value of the random variables that you can take. So the random variable can take different values, and the PMF gives a probability for each value to occur. And you can see that it's written as the P of X, small x would be a realization. If your sample space is 1, 2, 3, 4, then one way the probability of events X equal to small x for every event X in the sample space can be written in the PMF table here. So this is our sample space, 1, 2, 3, 4. And for each of them, we have its probability. And the summation of them is 1 because that's the whole sample space already. So this is how you read the table. X equal to 1, the probability of X equal to 1 is 0.2. Probability, if you want to calculate probability that X greater than 3, which means 3 and 4, right? You just sum up these two probability. You get the probability of X greater or equal to 3. So this is the probability mass function. It characterizes discrete random variables and gets its probabilities for each of the outcome in each value the random variable could take. This is just one example. Well, this function, this PMF, it ties the outcome with the probability. So this is the outcome, this is the probability. Well, this one is giving you like unequal probability, but when we're doing something like simple, when we roll a dice, it can be, like toss a coin. It can be either head or tail. So the probability for each is just 1/2. So n is the number of outcomes you can get. So you could only have 2 outcomes when you flip a coin. So the probability of getting either a tail or a head is 1/2. If you roll a dice, you have 6 outcomes, possible outcomes. The probability of them is 1/6. And we know from the axiom of the probability that sum up all possible value of X for their probability, it would equal to 1. And the probability would always between 0 and 1. Another example, it's a bit more complex for the PMF. See, we have 3 fair coins are flipped. We define the random variable X being the number of heads you observe. So you flip the 3 coins and you record the number of heads you observe each time you flip them. The possible values for X, it can only be like no head observed being 0, only 1 head observed, 2 or 3. It will not be out of this sample space. It can only be 0, 1, 2, 3. If you write each element of your sample space, write it out, like it would be like this. This is just telling you this is a sample space you have, and this is corresponding the random variable you're trying to capture from this. So this 3 head means 3 when you try to count the number of heads observed, right? And this is 2, you have 2 heads, and also you have 2. And this also you have 2, have 1, 1, and this one, if it's all tail, then no head, that's 0. And we know these are equally likely to observe because you have fair coins and you toss them, you can get any of them like with equal probability. And to get this PMF, you need first to get the total number of this X you can get from the sample space. So if you still remember, if we want to get this Px, it would equal to like this Nx over N. Capital N is the total number of outcomes you can get, which is 8 in this case. The size of the sample space is 8. And you have to get this Nx for each of this random variable in order to get this Px. So this is eventually what you get for the PMF. You will see examples like, or I mean, homework questions like this, asking you somewhat similar, asking you to complete a PMF. We can also plot the PMF, sort of plot, but they are simple. This is as a table, and if you plot it on a graph, so for each of the realization of your random variables, you just plot their probability, which is on the y-axis. It is the probability of x. So the probability of 0 is this 1 over 8. This is what a PMF looks like on a graph. Another concept is called CDF, sort of corresponding to a PDF, but what we will talk about is called PMF. PMF is for discrete random variables. PDF is for continuous variables, which we will cover for next week. And CDF is the cumulative type of PDF, but here we are talking about PMF, so CDF is a cumulative type of concept for PMF. We write it as capital X, which is the probability of the random variable X being at most X, small x. So write it like this, the probability of capital X less or equal to small x. So you just sum over all the probability of Y when Y is less or equal to X. So it's sort of a summation of PMFs. So if we use the previous example, the probability of X less or equal to 1, which is the probability you observe at most one head out of these 3 coins, would be a summation of the probability of 0 and probability of 1, which you just use this number, 0 and 1, you sum them up. That's 1/2. So this is CDF. It's a summation of some PDFs or PMFs in this case. Yeah, in the graphic, it's just showing you like the what it means. It's just you sum over like the all the values on the left of this small x, because it's capturing the probability that being at most x. So anything on the left, you sum them up. But this is just to show you how are they look like. This is the PMF, we see it already, and this is the CDF for this PMF. Like this is the CDF, capital F for x less or equal to, less or equal to 1. sorry, this should be less. So we have yeah, I think this is less or equal to 0, less or equal to 1, 2, and 3. Yeah. Right, because we only have this 0, 1, 2, 3 for realizations for this particular example. Okay, so next we'll talk about expected values and variance. Well, when we talk about expected values, we normally think it as the average. It's sort of equal to the average, but when we are in the setting of the probability, it has a little bit more complex. It's a bit more complicated in this case. I'd like to just show you all the things here. So the expected value is that, well, to put it literally, is the value we expect the random variables to take on, which if you want to compute it, you just take the sum of the possible values times their probability of occurring. So that's when those possible values have different probability for their occur. So when you calculate the expected value, just take the sum of the possible values times their probability of occurring. That's the expected value. Which formally define it, it's a random variable. The expected value of a random variable is the weighted average of the possible outcomes. Think it as the probability version of the mean. Weighted average, where each of the weight is their probability of occurring. If D is a set of possible value X can take, and P, X is the P and F, then write it mathematically as this EX equal to, this is the mu, also expectation value of this X, being the summation of X times PX. So this is the formal definition for expected value. A small example here, if you have a 1% probability of winning a $100 prize and get 0 otherwise. So you either get $100 or you get nothing. The expected value is that is 100 times the probability of getting 100 plus 0 times the probability of getting 0. So that's the expected value of the money you can get. Okay, so that's the expected value. For functions, so this is expected value for a random variable. But when we talk about functions, well, it follows the function rules that we know. If we have this hx being, expected of hx, it's a function of random variable. Our x is the random variable, and you take the expectation of it. It's just a summation over this hx, all the possible value for hx times px. And for a linear function ax plus b, like for example, this is our hx, and the expectation of it, you just do this a times ex plus b. Because this a is a known value, it's not random. B is not random. Only this x is a random thing. So this is what you do to get the expectation of a function of x. Okay, so this is the expectation, and like this definition is important, and this is important. So what about the variance of a random variable? Well, first of all, why do we need a variance of a random variable? We talked about the expected value of a PMF. Well, it's indicated where it's centered. That's sort of a weighted mean. So that's capturing where the data is centered. But just knowing the center is not really that informative about a whole data set. We also want to know like the ranges, how it varies from one value to another. So example here, here is a random variable with a 50-50% probability split between 0 and 100 would have the same expected value for a random variable with 100% probability of 50. So only knowing the expected value is not really enough. So we calculate the variance of the random variable as well to determine the spread, like the variability, or we call it dispersion. And if X, capital X, random variable, has a PMF PX and expected value mu, then the variance of this random variable, we write it Vx or sometimes VERX, or the sigma square is like this. This is the formal mathematical definition for a variance. It captures the variability and dispersion of your data. And the standard deviation of X is this small sigma, which is the square root of your variance. You will see why this capture the variability and dispersion. This is a different way of writing the variance or calculating your variance. And we know the standard deviation is the square root of variance, and that is the size of a representative deviation from the mean. So that's what the standard deviation means. So if the standard deviation equal to 10, then some observations will be further than 10 from the mean, some will be closer, but the typical distance will be just 10. So this is telling you what the variance is capturing, and most of the time the standard deviation is more easy to interpret because that's at the same unit of the random variable you're trying to understand. So that's just the typical distance that observation can deviate from the mean. Well, eventually we get to the some of the families for discrete probability distribution. But previously, what we did is just we manually assign probability with your realizations of the random variables. It is effective, but slow and not ideal. And lots of different situations and experiment types have somewhat similar pattern. So that's why we generalize the situation and we name them probability distributions. These are different types of probability rules that we can just say a random variable follows. So we always see some random variable follows some type of probability, some type of distribution. The first one we're going to talk about is the easiest, which is called Bernoulli distribution. And for random variables follows a Bernoulli distribution, we call it Bernoulli random variables. So this is what it means for a trial with two possible outcomes, either success or failure. We code a success as 1 and failure as 0. Then the probability of success we denote it as unknown value alpha. And it must be true that the probability of 0, failure, would be 1 minus alpha. And we call this alpha being a parameter for this Bernoulli distribution in this distribution. And we usually write this PMF as P with this bracket, X is your random variable, and this alpha is the parameters associated with this distribution. And yeah, we write it in this way to reflect that it depends on this parameter. So this distribution will depend on the parameter, this PMF. And if you write it out, it would be for x equal to 0, it equals 1 minus alpha. For x equal to 1, it's just alpha. And there's no other cases. It can either 0 or 1. So for other cases, the probability will be 0. So this is the first example of a probability family. And every value of alpha between 0 and 1. So it has to be between 0 and 1, right? Because that's a probability. So alpha is a probability of 1. So, so every different value of alpha would create a different PMF. So that is a number of this Bernoulli family of distributions. So this is why it's called a family. And it's each of the distribution would have its own parameter value. Well, a second distribution we'll talk about is the extension of the Bernoulli, which is called binomial distribution. So a collection of n Bernoulli trials, x1, x2 to xn, it is itself a new random variable. Y, we define it as y being the number of successful trials. So which is essentially just a summation of this each xi's. And each of this xi is like a success or a failure. Success being 1, failure being 0. So when you sum them up, that means the total number of success you get from this many trials. Yeah, think about this sum as adding up those ones for the successful values from this x. So this gives you the number of successes. And we have the following properties for binomial distribution. The probability of success in each trial is denoted by this P success equal to, this is again a parameter, the probability of success in each trial, in each of this trial. Each trial is independent of each other. So each of this X, so you flip a coin. The first time you flip a coin, next time will not affect each other. So they are independent of each other. And the order is not important for binomial distributions. It captures the number of success out of n Bernoulli trials. Yeah, similarly for binomial distribution, how do we write its PMF? Well, formally we use this B or sometimes BINOM. BINOM is like what R used. But for us, mathematically, we just write this B. This is telling you this is for a random variable X, and we have the parameter P and N for this binomial distribution. And for there to be X successes, there must be N minus X failure, because in total we have N trials. Some of them are success, some of them are failures. And each of the success have probability P, and each failure have the probability 1 minus P. And all of these are independent, so we can multiply them all together. So that's what we learned from chapter 2. If they're independent, we just multiply them. And order does not matter, so we just do this. We would choose, how to say this, n choose x. Yeah, so this n choose x you have this many of different options to have different combinations of have X number of successes out of this n trials. And then you times all the probability for each individual X. So yeah, I have this. We have X of this P being success, and we have N minus X of this being failure. So in total, we have N of this elements, multiply them together. We can do this directly multiplication because they are independent. Yeah, so write it more formally, it will be something like this. N choose X times P to the power of X, 1 minus P, which is the probability of failure, to the power of N minus X. This is the total number of failure. So this is the binomial PMF, and the parameter associated with this would just be P. And yeah, N is also considered as, N is just the number of total trials you have for this binomial distribution. Okay, so we want to get the CDF for a binomial distribution. And just following the definition of PCDF, it's a summation of this. So when X less or equal to small x, we write it as capital B. So that's the CDF, and which is a summation of all the summation of the probability of all events in this set. And this is probably more important for to get a better description of this distribution. We need to get what is expectation, the expectation of this random variable and the variance of this random variable when this variable is following a binomial distribution. And this is known once your P, the parameter is known, you can directly calculate it, the expected value of your binomial random variable, which is n times P. And the variance of it is n times P times Q, where Q is just one minus P. That's the probability of failure. Well, I think for this binomial, the important thing that you need to know is what is capturing is the number of successful trials out of this n Bernoulli trials. And each of the Bernoulli trials are independent to each other. And this is how you calculate its probability out of this binomial distribution. And also, well, you should know this, the expectation of this. Well, there are formal proof for this. How do you get this formula? But that's not really important for us for this class. You just need to know this is the expectation for binomial distribution, and this is the variance for a binomial distribution, distributed random variable. And you will need to use this over and over again. Okay, so this family of distributions each have their own set of parameters, and once the parameters are specified, then the distribution are fully known. Yeah, this is what it is, and there are many families. Like we talked about Bernoulli and binomial, that's the mostly often used. And there are like hypergeometric, there are negative binomial. Those are more complicated. We may not use it that often, but if you get into a situation where you need to use that distribution, at least you know, like for what is when we talk about distribution, what is that, and what are the different properties for them. So if you are interested in some more of the families, you're welcome to go to the book to find the mods. But in this class, we'll only cover this Bernoulli and binomial. That's what you mostly would need to use in your daily life, I guess. Okay, so this is the slide for chapter 3, and I want to go over a little bit of R today. Let me open the because I hope that you could use this R to help you do part of your homework, because it's really handy once you know how to use it. Let me log in. Well, yeah, I need to log into my what is this? I need to get Blackboard. Let's see. Yeah, this is Blackboard. Why take me here? Oops. Let me try this. Oh, okay, I found it too. Good. Well, it remembered. So this is our class, and this is how you get to your web assignment. Oh, by the way, I noticed there are 7 students registered, but there are supposed to 8. So one of the students have not registered for WebAssign, so that might affect your submission of the homework. So just be hurry up, because these are due soon, in 3 days. Well, the example. Oh, well. Before we go to that. Well, if I click it, then you might see the. Okay, let me go here first. Okay. Yeah. Okay, this is what I need to do. How do you calculate probability with R? Before we go to the homework. So is this, I think this is beginning. Let's take a binomial random variable x. Oh, no, x tutor here. X follows binomial distribution with parameter n and p. Or suppose the number of trials n equal to 6 and the probability of success for each of the Bernoulli trials is 0.2. If we want to calculate the probability of 3 successes, which is the probability of x equal to 3, we can do it in R with this function. D means the density. So density, or in R, is translated into English is just the probability in this case. So this is x equal to 3. This is the size of your experiment, which is n, and this is probability of each probability of success for each of your Bernoulli trials. So just by writing this, you will get the probability directly, even though I showed you how to do it like mathematically. But this is in practice how you do it in your homework. Well, there are some cases where you might need to do some like sum up of those PMFs, but this is when you do for binomial distribution. you do this to get the probability. And similarly, if you want to calculate the probability of 3 or less successes, written as p x less or equal to 3, you can do it with this p binom. Is q equal to 3, size again is n equal to 6. The probability is this probability of success being 0.2. So if you notice the difference here, this is q and this is x, and this is density, and this p is, or it's just a different language in R. But this p binom is giving you the CDF. Yes.
So for tests, are you really one?
Yes. Yes. Yeah, different way that you can do this is just ignore this argument like q equal, size equal. You can just write it directly. But I think the best practice you write this out, because sometimes it will be confusing, like when there are multiple arguments, but you put less than like required arguments, that will be problematic. Recommended way is to invest like this.
So Q on that example would be this maximum amount of time consider, right?
Yeah, this Q is this corresponding to this. And this x small x equal to 3 is this. So yeah, this is just an example showing you how do you do the binomial. Like when you know there are way many of the families you can do. Like in R, you just change this like binom to a different family, to like, negative binomial, like hypergeometric, those kind of things. But the R language, like D something, like in the future we'll do normal distribution. It will be like D norm, P norm. It will be just the same pattern. But here, it's just take the binomial as an example here.
You did also the binomial.
Yeah. Yes. Oh, great. I have this open. But how do I open it without having you guys see the? Let's see. Oh, good. There's no solution here. Well, I might edit it a bit. This is not the final homework you're going to work on. I might edit it a bit. Yeah, let's work on this example. Hopefully this R is working. Oh, this is something I learned like recently. I find each time you open the web sign, at least for me, from different computer, these numbers are changing. Well, I think for students, you should see the same numbers for your homework. But I guess for different students, you might see different numbers. Well, I think a quicker way to, because I have prepared one. This. This is strange. Because the number already changed, I have to change this again. So let's read this first. So NBC News reported on this date that 1 out of 20 children in the United States have a food allergy of some sort. Consider selecting a random sample of 20 children and let X being the number in the sample who have a food allergy. Then X is following binomial, so this bin is binomial with n equal to 20 and this p equal to 0.05. So it gives you all the information you needed. And if you it's asking about the probability of x less or equal to 3. Let's get to R. This is how I do it. I firstly assign those. Just in case some people might want to read it at the same time. So what I do, this is when I open it earlier today, it shows me n equal to 15, but now n equal to 20. So this is a good example showing you that if you do this, you assign this parameters first. So if you change, you just need to change the number once, then all this n and p would just use the value you assign to it. So now I know n equal to 20 and the p is 2.05. And for this, ignore those first because the numbers are off. Again, the numbers are off for now. Let's okay. So if you want to determine the probability of x less or equal to 3, or you just put 3 here, which is 1, and probability of x less than 3, that means the probability of s less or equal to 2. Also, that's why we put 2 here. We just run this. Yeah. You can also like run line by line. I just highlighted them both and run at the same time. So this gives you the probability. So the question you are going to see may not be the same number. So what I got here may not be the answer to your question. So yeah, this is the question A, and question B, the probability of x greater or equal to 4. So this is pay attention to the direction of this sign. So it's asking of x greater or equal to 4, which means you can sum over like all the realizations when x greater or equal to 4, which is 4 or 5, like up to 20, right? You can do yeah. By the way, this is the shortcut K. You can do Control Shift and C to comment one line, and you can also do Control Shift and C to uncomment it. If you use R a lot, you will find this handy. So this is what you can do to do this. Probability of x greater or equal to 4, that is summation of all the probabilities when this x greater than 4. So this is one way to do it. You just run it, you get this. And you can also, alternatively, you can also do this, but yeah, it is like the opposite of this probability of x greater or equal to 4 is the probability of x less or equal to 3. So beside 4 and above, it will be just 1, 2, 3, right? 0, 1, 2, 3. So this is alternative way to do it. You will get the same value, right? You just pay attention to the direction of this. Otherwise, you will get the right answer. Determine this probability. So between 1 and 3, you just, because we have less elements in this set, there are only 1, 2, and 3. We can just sum them up by doing this. Sum up all the probabilities. And expected value, and this where you just apply use the formula directly to get the expected value. As long as you can extract what is N, what is P from this statement, you are good to go. And pay attention, this is standard deviation, not variance. So that will be a square root of this. So this N times P times Q is the variance. The standard deviation is the square root of the variance. This is how you do square root. So in a sample of 80 children, what is the probability that none has a food allergy? None of them have a food allergy. So that's the so now N equal to 80. The probability of 0 would be, but sometimes I confused with, I got them messed up. Either it's P or it's D. Remember, this D is for a single probability, PDF or PMF, and this P is for CDF. Where here the probability of none, that's the probability of X being 0, right? So you just do this D binom, binom 0, N is 80. So I just put N and P. And this is how you work. Yeah, the only change is that your sample size changed. So N has changed. So I have to reassign this N. Or P did not change, so P is still equal to 0.05. So I just directly use this P. And this is the probability you use. I guess okay, I guess well, that's all the material I want to cover for today. And yeah, the homework 1 and homework 2 are due on Saturday, and homework 3, I'm thinking to have the homework 3 open just in case some people have already finished homework 1 and 2, so they have time to start looking at homework 3. But the due date would still be next week. I'll put it next Saturday so that you got enough time to work on it. Previously, I meant to do like each Wednesday, but that's might be a bit tight for some students. So then you will see another homework coming up, and it's due next Saturday. Yeah, I guess that's it for today. Anyone have any questions or any concerns?
Can R studio also help us with standard deviation?
Oh yes, standard deviation. Oh,
Because I use Excel, so.
oh
how
yeah.
I use R Studio?
Yeah, like for the first homework, you can actually use R. That's well, I didn't go over those because I thought those are very basic R, but that's something actually you can do it in R. But well, what you need to do first is you have to go out. Probably just give you a couple of well.
Like a very.
Yeah, it's like.
Yeah, you have to read the data into R. Some of them you can download the data directly.
Yeah.
well, once you save it into either a .csv or .txt, you can well, the best way, maybe not the best way, the usual way that you learn about a programming language, you just Google it, how to do this in R, how to read a .csv in R, you will find it. Well, this is very basic thing. You will find the answer, like when you read the CSV, you do read.csv. Or there are definitely some arguments. Like for example, Control C, if you don't know how to do this, you just do a question mark and run this line. It will show you, it will show you how do you like read a table, how do you read a CSV, where is your file and those things to read it in. But I'm thinking, well, I was expecting that people would be able to learn how to do those basic things, use R. So that's why I didn't go through it step by step. But this is what you can do. You can do Googling, and the resources that I provided on Blackboard are also great. I know there are lots of material, but if you search there, you can find what you want. Like once you read your data in, like those, for example, if you,
Yeah, you put that,
yeah,
you
if,
different numbers, and you do like STS. I'm like looking at the laptop, how do you have this to take all
yeah, like if you read your data in, like your file equals to, like you have to put the location of your file, and this will hopefully like read your data in already.
and it would put it in the environment.
Yeah, it will appear over here. Yeah, and when you do mean, you just do mean of x and standard deviation of x. Yeah, this. For example, I think there will be some example here. Like read.csv, this is your file. Ignore this. Yeah. So yeah, I believe you can do this, but if you have trouble, like you got error, I think it's great that people can like go to the discussion board and asking questions and help each other. And if you cannot get the help you want, you can always email me or office hour. Oh, for office hour, I have to say that for now it's over to office hour. I still didn't get my office key yet, so it's online.
We'll do the same thing.
Oh, you have, I think I put, yeah, on the syllabus, you have the office hour link for Zoom. Yeah, that's it for today.
Thank you.
No problem.
Yeah, I think it's